Okay, okay. So once again, we are talking about partial pivoting and how that is involved in LU factorization. So recall that in section 2.5, when you did your LU factorization, you didn't use any row interchanges when you reduced the matrix A in an to echelon form U. There were no row interchanges that were used, okay, when you got the matrix factorization L times U from section 2.5. But in fact, the book talks about in section 2.5, just after example 2, how in practical work, row interchanges are nearly always needed to do LU factorization because partial pivoting is used for higher accuracy. Now, partial pivoting is when you use the largest number in a column as your pivot. So what number are you used to using in a column as a pivot? What's a favorite number that you're used to using? What's a favorite number? What number, when you do row operations to reduce a matrix into echelon form or a reduced echelon form, what number do you use as a pivot? You use a 1. That's right, Cameron. That's right, Mikhail. So, but now they mention in the textbook in section 1.2 that the largest number, that in practical terms, we don't use the smallest number in a column as a pivot. We use the largest number as a pivot, and that's called partial pivoting. So this example here, and this this handout that a student gave me a long time ago in a computer science class, we have this system of equations, and the exact solution to this system of equations is x1 equals 40,000 over 39,999, and x2 equals 39,998 over 39,999. That's the exact solution, okay? But if we use a computer, the computer's going to use round off error, okay? So let's write this augmented matrix here. Let's write this system as an augmented matrix. Okay, there we are, augmented matrix. And let's use the point 00025 number as our pivot. So again, we're just thinking kind of like as humans, we're used to using small numbers as pivots in a column to produce zeros in that column. So let's use the smallest number, 0.00025 in the first column as our pivot. Okay. Now this is the opposite of a program like MATLAB does. MATLAB would use the largest number in the column as a pivot. But we're gonna work like human beings here. Okay. So okay. Now if we did a row operation here, what we would do to produce a 0 where the 1 is we would take the pivot, we would take the first row, multiply it by 40,000, add it to the second row, and put the result in the second row. Okay, so if we did that, this would be our row equivalent matrix. This would be our row equivalent matrix. Okay, see, we get a 0 here. But now what we're going to do, no, let's continue. So how do we get the negative 39,999? We take negative 40,000 times 1 and add it to 1. And then how do we get the negative 39,000? Oh, wait, there should be a 2 here. Thank you. Thank you. How do we get the negative 39,998 here? We take negative 40,000 times 1 and add it to 2. Okay? So far, are we good up to here, class? Please give me a thumbs up if you're good up to this step. Okay, thank you, Mikhail. Thank you, Cameron. All right, excellent, excellent. So, okay. Now, let's suppose that we used, that our computer is using 4 significant digits for the operations. It's storing 4 significant digits. Well, the 0.000025 is okay, because that's 2.5 times 10 to the negative 5th. So there's 2 significant digits being used there. The 1 is okay, that's 1 significant digit. This one's okay, that's 1 significant digit. This 0 is okay. But how many significant digits do you see in negative 39,999? How many significant digits are being stored? 5, that's right. So if we were to restrict, if the computer were restricted to 4 significant digits, what would it round negative 39,999 to? It's going to have to round it, right? It's right. It's going to round it to, it's going to round that to negative 40,000. Okay, and similarly, the negative 39,998, that also would be rounded to negative 40,000. No problem, Mikhail, that's fine. So the computer, you know, it's an automated thing. It's going to use its significant digits for rounding. And so the computer is not going to give you this, the augmented matrix here. It's going to round those 2 values to negative 40,000. And keep in mind what the exact solution is. The exact solution is basically almost equal to, x1 is almost equal to 1, and x2 is almost equal to 1. Okay? So let's see how well the computer does in getting an answer like that when we used the smallest number in the first column as the pivot. Okay, like we humans do. Okay, well, if we go to the next page, okay, here is the, and you can blow this up. You have a thing to blow up the page, to expand the page. Here is our system. Here is our system. And a lot of the information in this paragraph here, well, we just talked about that, because here we are with this system here. So if you solve that system, okay, if you solve that system, x2 will equal 1. Okay, x2 will equal 1. And then you take 1 and substitute back in the first equation. X1 would equal 1. Hold on here. Let's, one moment. Hold on. Keep the 1 there. Okay. So x2 will equal, or x1 will equal 1 minus x2 over 0.00025, and that's going to equal 0. That's going to equal 0. So do you see this? You see this, everybody? All right, you see what I'm doing here? So what I'm trying to do is I'm focusing here. I'm focusing here. And x2 is equal to 1, and x1 is equal to 0. Because if you put right here, x2 equals 1 in here, you're going to get a 0. But remember, the correct answer was x1, it was approximately 1, and x2 was approximately 1. So how did we do? Okay, this is the how was our answer? x2 equals 1 and x1 equals 0. How did we do? Did using the smallest number as a pivot in the first column, the 0.000025, did that do a good job for us? Or did it do a bad job for us? Well, yeah, Mikhail says our error got magnified. Okay, this is a poor answer, right? This is a poor answer. Okay, you're not going to hit the target, so to speak, with that kind of answer, right? So what we should do is use an exchange step, okay, or a interchange step. Interchange the rows, okay? Make the second equation your first equation, and your first equation your second equation. And then you can use the 1 here as your pivot. And I'm sorry, I don't want to write over, I'm just trying to, maybe let me go to 1 point. Yeah, so here, what we did was we took the equation on the previous page. We took the equation on the previous page here, the system of equations. Okay, don't worry about this above, right? We took this system of equations and we interchanged the first and second equations. That's like interchanging the rows, right? And we interchanged the rows. Okay, we interchanged the rows so that we would get then in the first column the 1 here, the 1 here as our pivot. Because, well, no, I'm sorry, I should be looking here, right? This is where let me erase it, hold on. Here's where we are. We interchanged the first and second rows of the system of equations. And now the 1 here is the pivot we're going to use. So far, are there any questions? Please let me know. Please let me know. Marcella, how are you feeling about this? Are you comfortable? Okay, good. Jonathan, how about you? Fatima, how about you? All right, well, Belen, how about you? You're good with it? Okay, all right, all right. Yasin, how about you? I should give everybody 100 points just for answering this question, right? You know, just as a, all right. Well, anyway, all right. So now what we're going to do, well, I just appreciate your, just thank you. Okay. So now what we're going to do is we have to do row operation on this. So what are we going to what would the row operation be? Let's look at our result here. So they obviously did a row operation to go from here to here. So they got a 0 here in that spot. So they took row 1, and what did they multiply row 1 by? If you're gonna get rid of this point, if you're gonna get rid of this 0.00025, and you use the larger number 1 as the pivot, what are you going to have to multiply row 1 by? How about negative point? Good. That's right, Mikhail. Negative 0.00025. So negative 0.00025 times row 1 plus row 2, put the result in row 2. So the first row stayed the same. And what happened though here? The one here and the one here didn't change. Now, why is that? Well, let's talk about that. Let's talk about that. So if you focus on this one here, 1 minus 0.00025 is 0.999975. But using 4 significant digits, that's going to round to 1. That's going to round to 1. And similarly, for the one here, why is this a 1? Well, what did you do? You took negative 2 times 0.0025, there's the 2 there. You took negative 2 times 0.0025 and added it to 1, because remember, this is the row operation you're doing. And that's going to give you 0.99995. That rounds to 1 using 4 significant digit arithmetic. Okay, so if you look now at this resulting system here, if you solve for x2, you get 1. And if you solve for x1, you get 1. See that? And so that is a much better, it's an approximation, because x1, the exact answer for x1 is 40,000 over 39,999, and the exact answer for x2 is 39,998 over 39,999. But using the larger number, the number 1 there, okay, using this 1 here as a pivot, as opposed to the 0.000025 smaller number as a pivot, you got a much more accurate answer. You see that? Does that make sense? And this is the idea behind partial pivoting. This is the idea. Are there any questions on that? Okay, one moment here. I'm looking for, hold on everybody. Just got to find it. There we go. This is what I want. Okay, so, I mean, seriously, are there any questions at all? I mean, do you see, this is just a little like kiddie example to show you why programs like MATLAB will use the largest number in a column as a pivot to produce zeros below it when row operations are done. It's so that it's to reduce round off error. It's to reduce round off error so that your answer, your approximate solution, will be as good as possible to the exact solution. Okay, Nell, how do you feel about that? Are you comfortable with that? Okay, Mikhail's good. All right. David, how do you feel about that? I'm just trying to see if you're okay, if you're feeling all right with this. Okay, well, I appreciate those of you that are, responding and everything. All right, well, now, let me go to the book here. Let me go to the book. So in the book, they talk about how in practical work, row interchanges are always needed to reduce the matrix A to echelon form U. So in the LU factorization that you've experienced in section 2.5, you've not done any row interchanges. But as you saw in the example we just looked at there in the handout, a row interchange was needed in order to do the partial pivoting. Okay, and so in practical work, this is a comment in section 2.5, right after example 2. In practical work for LU factorization, row interchanges are nearly always needed because partial pivoting is used for high accuracy. Okay, recall that this procedure selects among the choices for a pivot an entry in the column having the largest absolute value. To handle row interchanges, the LU factorization that you learned in section 2.5 can be modified easily to produce a lower unit triangular matrix that is permuted lower triangular. Okay, and you're going to use then something called permuted LU factorization. Okay, now let me just bring up one file here. Permuted LU factorization. Let me just bring it up. Give me just one moment here. What I'm doing is I'm going to MATLAB assignment number 2. And I want to just show you now how this relates to the first exercise. Okay, so if I share this, okay, can everybody see MATLAB assignment number 2 okay? Give me a thumbs up if you're seeing that all right. Okay, thank you, Yasin. Thank you, Marcella. Thank you, Cameron. Thank you, Mikhail. All right, so this, of course, is what you, for finding the determinant of A, that's a formula that you learned from section 3.2, properties of determinants. And the LU factorization that you're used to seeing, the LU factorization that you're used to seeing is A equals L times U, right? But now they're saying P times a matrix P times A equals L times U. And the matrix P is called a permutation matrix. So if P equals L times U, and you take the determinant of both sides of that equation, you're going to get this equation, determinant of P times determinant of A equals determinant of L times determinant of U. Okay, that's what you're going to get. Now, this means that the determinant of A would equal then, if we take this equation and divide by the determinant of P, you'd have determinant of A equals determinant of L times the determinant of U over the determinant of this permutation matrix P. Well, what's the determinant of L? The lower unit triangular matrix. What's the determinant of L going to equal? So it's a triangular matrix with all diagonal entries equal to 1. Okay, what is that diagonal product? What is that diagonal product? Mikhail? Or anybody? The determinant of L? The diagonal entries are all 1s. It's going to be just 1. That's right. And good. And the determinant of U is just the determinant of U. That's going to be the diagonal entries of U. And the determinant of this matrix P at the bottom, it's a permutation matrix. That's just going to be either plus or minus 1. And so the determinant of A, L is the one with the 1s of the lower unit triangular matrix. That's right. That's 1s on the diagonal. So you see the determinant of A is equal to plus or minus the determinant of U. Okay, and that's what you're going to be in this first exercise in MATLAB assignment 1. You're going to be checking the result. You know, you're going to use MATLAB to get the determinant of A, and you're going to check the result. You're going to check the result by taking the determinant of L times the determinant of U divided by the determinant of P. That's how you're going to check the result. Now, what we'll do in the next class is we will actually look at an example where we will look at one of these permutation matrices, because the determinant of the permutation matrix, right, is going to equal plus or minus 1. Well, how do we, you know, when's it going to equal positive 1? When's it going to equal negative 1? So I want to do another example. When we meet on Wednesday, I will do another recording that will actually go through an example where we have a 3x3 matrix. We use MATLAB to do the LU factorization, and you will understand what the matrix, you know, it's going to give an output. This command here. This command here in exercise 1, LU of A equals, on the left, the matrix with LU and P. You're going to understand what, well, you're going to understand what P means. You already know what U means and what L means. So you're just going to have you're going to have a deeper understanding of what the exercise 1 is talking about. But now you understand at least the foundations behind what we're trying to do here with the permuted LU factorization. Are there any questions before I stop this recording? I'm going to place this recording incidentally with the MATLAB, with this MATLAB assignment number 1 in Blackboard. Okay, P, Mikhail, is called a permutation matrix. It's called a permutation matrix. It's a matrix such that when you multiply it by the matrix A, okay, how do you find it? How do you find it? How do you find this permutation matrix? I'll show you. I'll show you. But permutation matrix P is going to simulate the row interchanges you need to do so that your pivots are the largest numbers in each column. Okay, when you do the when you reduce the matrix to echelon form. Remember, multiplying a matrix, say, by another matrix does a transformation, and the matrix P will simulate the row interchanges you need to do so that you're using the largest pivots in each column. Okay, Mikhail, does that answer that question? Okay, all right, so you're welcome. So we will then now look at an example on Wednesday so you can see an LUP factorization in MATLAB. Excellent. Let me stop the recording. Thank you for staying a little bit longer. Thank you.